Now, in the previous part, we saw how the notion of a complex number was gradually accepted over several centuries. And we also saw the beginnings of some kind of analysis with complex numbers, the substitution of complex variables into real integrals in order to solve them, and so on. So this is where we're going to start now with the story of complex analysis. So Johann Bernoulli, Euler, and others were quite freely using complex numbers in this kind of context. But of course, the question then arises as to whether this is valid, whether this is a valid substitution to make. Now, Euler, in a text published posthumously, argued yes. He remarked that this is a very useful technique, which nobody was disputing, and that you can check your answer by doing it a different way. So the same sort of justification as was given for some of the methods of the early calculus. You can check this in other ways. Similarly, Laplace, he experimented with different integrals and seemed to prove that this method did work. So he argued yes. Poisson was starting to have doubts, though, by 1812. So he was asserting that all the results that you get should be confirmed by direct calculation. So once you've got the answer through complex methods, you should then check it, which seems reasonable, but at the same time, it's going against these slick new methods that people were very happy to have at their disposal. And so then we come to Cauchy. So he was inspired by reading what Laplace had written on this subject. He set about trying to determine whether it really was valid to make these kinds of substitutions and to prove that it was valid to make these substitutions. And so in doing so, he created a lot of the complex analysis that we now learn. So regarding the history of complex analysis, there are some accounts of it in Katz. There's also a book on it by Frank Smithies, which contains some primary material. But another book that I would also point you towards is one that I've already mentioned in connection with the development of real analysis, and that's this one by Jeremy Gray. And so it's a history which develops the history of analysis, both from the point of view of the real and the complex intertwined, which is a slightly more realistic version of the story than perhaps the one that I've told, because they developed in conjunction rather than separately. So let's have a look at some of the things that Cauchy did to earn this title of creator of complex analysis. And so perhaps the next few slides are going to just seem like a bit of a catalogue of Cauchy's mathematics. So he looked at results relating to integration along paths and contours. So in particular, the fact that an integral along different paths between the same 2 points is equal regardless of the path, provided there are no singularities there. And so he began with some attempts to justify these ideas, and his work features certain assumptions like the Cauchy-Riemann equations, which were in there but weren't emphasized as a fundamental part of the theory. And you notice that I've given 2 dates for this paper. It was written in 1814 but wasn't published until 1827, and that's because the referees at the Academy were not entirely convinced by this, or not entirely convinced by the value of this, because a lot of what Cauchy seemed to be doing was just analysis in the real plane rather than the complex plane, so in R2 rather than C. And so they wanted to know what was new about this. So he spent some years redeveloping the ideas and seems to have developed a deeper understanding of what was going on. In 1826, as you'll have seen, having come to the essay that's marked for week 7, he was developing the calculus of residues. So if initially when looking at contour integrals he was avoiding singularities, he now has to acknowledge what happens when you have singularities on the path or within a given region. So this is essentially how to handle functions when they become infinite. The integral formulae that you see when you learn complex analysis also came along a few years later. In this case, in the context of celestial mechanics. So this was very much a computational tool for Cauchy at this stage. A lot of what he was developing in terms of complex integration was done from a point of view of calculation, of solving integrals that could not be solved through other methods. And in a lot of what he was doing, he was trying to mimic the real calculus, the real analysis, And so he was bringing infinitesimals across into the complex setting, and so perhaps carrying some of the problems across with that as well. When it came to adapting ideas from real analysis, of course, he wants also to develop ideas about power series, and so Taylor series expansions for complex functions emerged in his work. And as I've just said, one of the major applications that motivated him was the desire to evaluate certain definite integrals of real functions. And so you see a lot of progression, or a lot of changes anyway, in the way that Cauchy handled complex numbers and complex variables. And so his ideas about what a complex variable actually is changed over time. So he began at one point by thinking of them as being formal numerical expressions governed by certain rules. So the rule that the square root of -1 squared is -1, and you could just do algebra with these quantities. He then began to shift to a more geometric and perhaps more intuitive idea about complex numbers. Intuition only takes you so far, as you know, but perhaps there's some of this thinking going on here. And so, of course, then in this setting, he had to start thinking about multifunctions and restricting to relevant branch cuts and so on. And there's also another method, which I won't dwell on, because perhaps needs some material from the Rings and Modules course to appreciate this fully. But he set I equal to the square root of -1. He called it a real but indeterminate quantity. What he meant by this is perhaps not immediately clear. And so he's just reducing the root -1 to a symbol, essentially. And so we don't need to torture the mind with what it actually means. So in modern terms, what he was doing was he was working in a field where we're factoring out by I, the polynomial I squared plus 1, but let's not worry too much about that here. Another change that you see is the way that he viewed the complex variable. So first of all, like a lot of people in the 18th century, beginning of the 19th century, a complex variable was something made up of a real and an imaginary part. And so this is where the distinction between what he was trying to do for complex numbers and what you can do in R2 is a little bit blurred. But later on, he started to think of a complex variable as being just a single quantity z in the way that we often do nowadays. So his first memoir, this 1814 or 27 one, begins by discussing the concerns that Laplace had raised about this passage from the real to the infinite. And then he sets about trying to solve difficult integrals. So the one on the slide, for example, which is equal to pi over e, in case you're interested. And he developed some very powerful techniques for solving integrals like this. Along the way, he noted the Cauchy-Riemann equations in passing. He wasn't the first person to do so, but he noted them. So in order to ensure that a derivative of a complex function is well defined. But he noted it in passing as a useful general property rather than being a fundamental feature of the theory, which we tend to regard it as nowadays. So he regarded it as a useful property of analytic functions, where analytic in this context means a function defined by algebraic operations. So a function for which you can write down an expression, even if that expression is an infinite series. In his Cours d'Analyse, he starts to, this is where he's looking at complex numbers as symbolic expressions of the form a plus b root -1. He gives 55 pages of formal definitions and develops the properties of complex numbers, and also starts here, also later on when he's thinking more geometrically, starts to think here about multifunctions. So what are the most natural branches of functions to take in order to ensure that you have a well-defined single-valued function. At all the time, he's seeking to extend ideas from real functions to the complex case, particularly power series, because they're so useful in the real case. And so this is where ideas about convergence, and he's realizing the important role that is played by the modulus of a complex number. So that's where these ideas are starting to come in. In 1825, in a second memoir, he's thinking about complex integration and, in a very bold and direct way, adapting his definition of a real integral, which we saw a couple of lectures back, to the complex case. So it's starting to look something like this. He's defining his integral to be the limit, or possibly one of the limits, of the sum of products of the form on the slide. So you can see this is looking like an adaptation of his notion of real integral. These are, in some sense, this is a sum of rectangles, but of course here the interpretation is difficult. The ideas about area don't quite work as they do in the real case. He doesn't give any explicit definition of a function of a complex variable here. He's sort of assuming that it's differentiable in some sense, doesn't quite define what he means by differentiable in this context. And so in the background, we always have the Cauchy-Riemann equations. So having developed his notion of complex integral, he can look at contour integration, and he can prove this what is to us a very familiar result, that in any domain where the function does not become infinite, the value of a complex integral is independent of the path along which it is taken. So we tend to phrase this in terms of loops, of closed paths, but Cauchy was thinking instead about two fixed points and then taking two different paths along those paths from one point to the other. So he's sitting within a rectangle. That's a restriction that we can eventually get rid of. So provided the integral does not become infinite anywhere nearby, we can prove that the integrals along these two paths are the same. So adapting that to the context in which we would look at this, of course, the integral around the contour is 0. And so that the path is independent, that the integral is independent of the path. And this is one of the things that his referees question. Is this really a theorem about complex functions of complex variables, or is it just about real functions in the plane? So this is something that Cauchy had to settle. And it's worth noting in passing that Gauss, in fact, had also developed these ideas in 1811 alongside a definition of a complex integral, but he didn't publish, which is a recurring theme in a lot of 19th century mathematics. Gauss got there first, but he didn't actually publish. So having dealt with contour integration where there are no singularities in play, Cauchy, of course, then has to turn to the question of what happens when the function becomes infinite. He looks at this limit, as you've probably seen from writing the essay about the calculus of residues, and he essentially has to look for a correction term to the integral when it becomes infinite, and he finds that this 2 pi f root minus 1 appears. And so he can extend this to multiple singularities or higher order singularities. And so this is sort of an ancestor of what we now call the residue theorem and the calculus of residues. Moving to Taylor series for complex analytic functions, we know that he did this in the real case, so he begins to extend this to complex functions, and he says that a complex function has a convergent power series if it is finite and continuous. What he meant by that is not entirely clear, but it seems to cover something like the modern notion of holomorphic, because that's what you need in order for this to work. And he kept refining this theorem over many years. Eventually, the idea of differentiability becomes explicit, where it wasn't at first. And although the language that he uses, there's still verbal expression of a lot of his ideas, which leads to ambiguities. It's not necessarily satisfactory to modern eyes and has some of the same problems as existed with the real analysis at this point, because he's just carrying ideas across to the complex setting. He's still considerably more rigorous than what a lot of other people were doing at this time. Eventually, 1841, he extends this to negative powers as well. So this is where Laurent's theorem comes in, with application then back to calculus of residues and so on. And this was seemingly also proved independently by Laurent, which is why his name is attached to it. So I've given you a catalogue of things that Cauchy did. And so we see his ideas developed over many years. They went through various different iterations. And we might ask certain questions, which I'm not really going to answer now, but we can ask certain questions about his ideas concerning complex functions. So did he really appreciate the fundamental nature of some of the concepts that he was developing? So the thing I have in mind is the Cauchy-Riemann equations. So he didn't put them front and center in the way that we might do. So did he appreciate that these were really fundamental to the theory? And did he recognize the subtleties of the distinction between working with complex variable or simply working with pairs of real variables? You might say that perhaps at first the answer to that is no, but that over years his understanding developed. And having said all this, perhaps we might question whether historians of mathematics have read too much into Cauchy's early work on the basis of what came later. So now we have we might flatter ourselves by saying we have a deep understanding of complex analysis, and then we transfer back our knowledge onto what Cauchy was doing. He did eventually manage to develop some of these ideas, but are they really present in the early forms in which he wrote them down? And I don't have a definitive answer to that question, but it's something we might just like to think about. And so just a final point to note about Cauchy is that he is credited, rightly for the most part, with many of the fundamental ideas of complex analysis, but it doesn't necessarily mean that they appeared fully formed. So these are ideas that developed over several decades in Cauchy's work. Now, the other name that I will mention just briefly in connection with complex analysis, there are several, but one that I should mention is Riemann. So in his doctoral dissertation of 1851, he starts from the idea of a complex variable as a single quantity. So this is an idea that Cauchy only came to later on. And he gives the first formal definition, really, of a function of a complex variable. And in particular, what it means for that to be differentiable. So in essence, he's asserting the existence of the same limit that we look for when we're thinking about complex functions. And so there are various things in this dissertation. The Cauchy-Riemann equations you can see at the top of this page here. They appeared on page 4, so they're presented as being very fundamental to the theory. And then there are lots of other familiar ideas in there, holomorphic functions, conformal mappings, and so on. But in fact, the impact, at least the early impact of Riemann's work was quite limited by the abstraction with which he presented these ideas. So he emphasized what you might call the topological properties, so the connectivity of the complex numbers, for example. So he's doing complex analysis, again, in the way that you learn it, because you learn it in the Part A course, first by setting up a lot of theory connected with metric spaces, and then using that to go on to do complex analysis. And this is very much like the way that Riemann was doing it, but it was too abstract for many readers at this time. So the early impact was limited. The publication was not particularly widely spread, but it was reissued. This dissertation was reissued in 1867 and was more widely read from that point onwards. So I'm going to bring this lecture to a close, and in fact the discussion of analysis within the course to a close, with just a couple of slides looking at the meaning of some words that we've used through the past few lectures. This is partly by way of summing up some of the things we've seen, but also I'm going to use this to point towards things that we'll look at next term in the reading course. So what I'm going to pick up on is the use of the word analysis and analytic. So we've seen the classical idea of analysis as being a method of solving a problem as opposed to synthesis. So synthesis, very constructive. Analysis was this sort of reverse process whereby you build from the thing you want to prove in the hopes of being able to arrive at a known truth and then reverse the steps and thereby construct a proof. So that's the sense that is in the background around 1600, when people are starting to do analytic geometry. So the analytic art and analysis at this point simply meant solving finite equations. Later that century, of course, Newton and others are starting to apply techniques that apply to finite equations to the infinite case, particularly to infinite series. So we're starting to see the word analysis shift from the solving of finite equations to something to do with infinite processes. Certainly this is the sense in which Euler is often using the word in the following century. And it's interesting to note the way in which the word analysis is used in the sections of journals. So in France, for example, the Academy split the mathematical parts of its journal into analysis and geometry. So analysis and geometry both referred to pure mathematics in a broad sense, but analysis tended to mean algebra, calculus, something more algebraic, whereas geometry was a bit more practical, perhaps with a spatial bias, as you might expect from the word. But then by the time we get to 1821, Cauchy's Cours d'Analyse is really using analysis in very much the way that we would use it today. And I'm making that judgment based upon the content of Cauchy's textbook, because it looks like the analysis that we do today. So that's analysis, and perhaps analytic in some sense. But we also have the notion of an analytic function. So the term is first being used at the end of the 18th century. So for Lagrange, a function is analytic if it has a power series expansion, which is the sense in which we would use it. But for Lagrange, this is for subtly different reasons. He's using the word analytic in an algebraic sense, in this older sense of being able to write down an expression for it. And in the infinite case, that means it has a power series expansion. So his use of the word analytic function, the term analytic function, does tally with ours, but not quite for the same reasons. A bit later on, when we're moving into the complex setting, Cauchy he's not using any special terminology, but he's looking at functions that we might term analytic, and looking at functions that are continuous and that satisfy the Cauchy-Riemann equations, which is always true of analytic functions in Lagrange's sense. Riemann, as we've seen, switches to focus to this limit-based definition of an appropriate function. Weierstrass then begins to pull things together, putting it into more of an epsilon delta type language, using Lagrange's term analytic, but with Riemann's notion of a function. And then, of course, the way that we do things nowadays, we're following Riemann and Weierstrass, and we introduce lots of other words, so holomorphic and meromorphic and so on. But they're all variants of this word analytic that has been used over the last couple of centuries to refer to some form of differentiability for complex functions.